Okay, so moving along here, our next little unit that we went into, 4-6, was you learning how to complete a square to make a perfect square trinomial. And we first kind of explored this by having you guys think about what is a perfect square. You know, perfect squares like, let's see here, 25. You know, 25 is a perfect square, 49 is a perfect square. Reason why they're perfect squares is because that's 5 squared and that's 7 squared. Polynomials are absolutely no different. If I had a polynomial like this, x squared plus 6x plus 9, that would be considered a perfect square, because if I tried to factor and think of two numbers that multiply to 9 and add to 6, it turns out to be the same duplicate number of 3. So that would make x squared plus 6x plus 9 a perfect square. So we have something called perfect square trinomials, and with perfect square trinomials we can actually look at trying to complete the square to be able to factor it as a perfect square. And so when you look at something like this, what you're looking at here, especially when it comes to completing the square, key thing is a has to be 1 to complete the square. But if we have an ax squared where a is 1 and bx, and then isn't this really where c used to live, which is c right there, ax squared plus bx plus c. What they're essentially trying to tell us here is that we can get that c value. C can be found if we take b, cut it in half, and then square it. And after we do that, that'll allow us to get that c value to complete the square. So a couple of examples, if I look at, say, x squared plus 14x, to complete the square, we take the 14, we cut it in half, and then we square it. So then that would be 7 squared. So completing the square would be 49, which would allow us to write x plus 7 squared. Okay? So if we were to look at something like this one over here, what value would complete the square for this expression? Well, what we want to look at is look at that b value, and notice that b is -4. And so to complete the square, we take b, cut it in half, and square it to find c. So that would require us to put in a -4, divide that by 2, and then square it, which would take us to a -2 squared, which would give us a 4. And that's actually what our c value should be. So to complete the square, we'd have x squared minus 4x plus 4. And that would allow us to write a factored form, which would look like this: x plus, or not plus, because we have a subtraction sign going on there with the minus 4x. It makes sense to write x minus 4 times x minus 4, or better yet, known as x minus 4 squared. So the correct answer, what we're looking for on that, is I'm looking for that 4 there to complete that square. Okay, we'll come back to this a little bit later in future lessons on how we can use completing the square not only to solve quadratics, but to work with conic sections as well. Now, this next problem here, quadratic formula. What is that quadratic formula? Just the general version of completing the square when a is actually not 1. And so then it looks something like this, right? To solve for x, it would be the opposite of b plus minus the square root of b squared minus 4 times a times c, and that's all divided by 2a. You know, I want to talk here, and I didn't get a chance to talk to you guys about the review about this, about one of the big pitfalls I'll see with students when it comes to the quadratic formula. First of all, let's write down what a, b, and c are. So a is -5, b is 5, and c is 2. First off, another one before we keep on going is realize that this can't get factored with GCFs. And secondly, if we tried to multiply those together, I don't know if we'd be able to come up with two numbers whose product is -10 and their sum is 5. So being able to factor this by grouping would not be possible. So we need to have the quadratic formula here. So to set that quadratic formula up, we'll have x equals the opposite of b. Well, if b is 5, we're expected to put a -5 right here. And then plus minus the square root of b squared. In this case, b is 5, so I'll write down 5 squared. Even though I know it's 25, I'm still just going to follow the formula here, because that'll help keep my head on straight as I go through the rest of this, because there's a lot of stuff going on here. And then times 4, or minus 4, times a, which in this case is a -5, and then c would be 2. And then we're going to divide by 2 times a. In this case, a is -5. Okay, so as I talked about in class, the most effective strategy that you can do here to help simplify this really, really elaborate expression is realize you have grouping symbols within grouping symbols. The fraction bar groups up the numerator, so we have to work up there first. But secondly, the square root groups up all this stuff right here. So we're going to want to figure out what 5 squared minus 4 times negative 5 times 2 is. Quick work with your graphing calculator can help you out with that. So as you can see here, I typed in the 5 squared minus the 4 times negative 5 times 2. Do you notice I left the square root out of that expression when I typed that in there? It's very important. All we need to know is that underneath the square root is we have 65, which we can now go ahead and put into our next level of our quadratic formula. Which here, I'm going to point out one thing I do see a lot from students when it comes to this fraction bar. I'll see a lot of students do this, where they'll write that negative 5, and then the plus minus will come in, and then they'll have the square root of 65, and then notice down there we have negative 2 times negative 5, which would make negative 10. They like to put that negative 10 right there. Okay? They cut that fraction bar off too short. See in that quadratic formula right there, see how that fraction bar even goes underneath the b? So be absolutely sure that when you're doing the quadratic formula and you're showing your work, make sure that fraction bar goes over the entire thing, even that negative 5 right there. So both of those two guys right there, let me even move over that negative 10, kind of center it over that plus minus sign. There we go. Okay? Now, that square root of 65, here's what I will let you guys do at this point. 65 is not a perfect square. So, what we're looking for right here are two solutions, and we have both of them right here. So, you can leave your answer just like this. The reason why is because it's the most precise answer. Understand what's going on here with these problems is that there's two solutions. One of them, x could be equal to negative 5 plus the square root of 65 divided by negative 10. The other solution could be x equals a negative 5 again, but minus a square root of 65 divided by a negative 10. Now, I think the math community would get kind of upset with me if I didn't mention this, so I'm going to mention this. See how this guy is a negative, and this guy is a negative, and this guy's a negative, and this guy's a negative? Technically, we could simplify this even further and write something like this, but I want you to notice something. I'll put it in purple. If I divide each one of these terms by that negative to make everything positive, I'd get a statement that looks something like this. 5 minus the square root of 65 over a positive 10, and then this one over here would say 5, divide that one by the negative, so it would be plus the square root of 65 divided by a positive 10. Mathematically speaking, this would probably be the most simplified answer. I'll let you get away with this one over here just for now. There will be a time and place where we're looking at some more simplified answers, but since we're just getting introduced to that quadratic formula, I'll let you leave it there. Okay?